If we look at this chemical equation, anything that is on the left side of this equation, so all of this stuff here, is also known as reactants. The yield sign, okay, that arrow, that is the same thing as saying equals to. Okay, this is a numerical equation if you want to look at it like that. And everything on the right side of this equation, these are known as products. So what we're saying here with the law of conservation of matter is that the reactants in any chemical equation, the amount of reactants, and we're talking about elements and numbers of atoms of those elements, whatever's on the reactant side has to be equal to whatever's on the product side. You can't make atoms out of nothing. Okay, you can't get rid of atoms if they're there on the reactant side. One way of doing this is giving these substances amounts. If I said that I started off with 36 grams of glucose, C6H12O6, and I added, I don't know, let's give it 12 grams of oxygen, that would give rise to, 24 grams of CO2, and how many grams of water? Can you solve a problem like that? Yes. How do you solve for X? The law of conservation of mass states that whatever you start with, whatever reactants you have to have the same amount and the same kind of products. So if I tell you that you've got 48 grams of reactants, you're going to need 48 grams of products, and you only have 24 there. So, by taking this 24 and bringing it over to this side, we end up subtracting by 24, and that's going to leave us with X being equal to 24. Because both sides here have to be equal, right? So this is one way of doing a law of conservation of matter problem. Another way comes with balancing equations. When we look at balancing equations, okay, having an equation that is balanced means it's going to have the same number of elements and the same number of atoms on both sides. This is often the type of question you get. Okay, they'll give you a numeric or a chemical equation and they'll say, okay, balance this equation for me. And the way you have to do that is you have to count the number of different kinds of elements and the number of atoms of each of those elements on both sides of the equation. And here's the deal. If they add up, great. Okay, in this equation, we've got 3 different kinds of atoms. We've got carbons, hydrogens, and oxygens. Okay, if you look on both sides of the equations, all 3 of those elements show up. Counting the number of each of those elements, making sure they're equal on both sides, means, and if they are, that means that the equation is balanced. If they're not, there's a few things that you can do. Okay? You can never, ever, ever, ever change the number of subscripts that are here. These numbers, they're stuck there. Okay? You can never add small little exponents like that. But the one thing you can do is you can add large numbers in front of actual groups of elements. And by doing that, this is basically the same rules that apply to exponents in mathematics apply to equations when you're balancing them. If I have something like CO2, how many elements do I have there? I've got 2 elements. I've got carbon bound to oxygen, correct? Now, if I ask you how many atoms of each do I have? How many atoms of carbon do I have? I only have 1 carbon atom because there's no little number here, okay, and there's no number in front. So I've got 1 carbon. How many oxygens do I have here? I have 2 because this little subscript right here is behind the oxygen, which means it applies only to the oxygen. Okay? So I've got 2 oxygen. So what's my total number of atoms in that molecule? I have 3 atoms. Now, if I sit here and I put a big number in front of it, okay, that's the same thing as saying that there are brackets around this whole thing. And if you put a whole number in front of a bracket, what does that mean you do to everything inside that bracket? You multiply it by everything inside the bracket. So in this case, this means that you're going to have 6 times the carbon, and you're also going to have 6 times the O2. Okay, because the little 2 there is in that bracket. Okay, so now, how many carbons do I have? I have 6 carbons here. How many oxygens do I have? I now have 12 oxygens because I already had 2. And if you multiply 6 by 2 oxygens, you get a total of 12. Okay? So that ends up being 12. So when you go about balancing equations, you basically have to make sure that the number of atoms on both sides of this equal sign right here are equal to one another. If they're not, then that equation is not balanced and it is incorrect. What the actual number here is saying, okay, what this 6 is saying, is it's saying that there are, in this chemical equation, there are 6 CO2s. Okay, CO2, 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 and another. Okay, so this is what this is saying. That when you're looking at the breakdown of basically glucose, okay, which is broken down with the help of oxygen, it gives you 6 CO2s. And this makes sense because if you look up here, how many actual carbons are in the glucose equation? C6H12O6. Okay? If you look at C6H12O6, on this side of the equation, there are how many carbons on the reactant side? There are 6 because this doesn't have any C's in it. The only C is this guy right here. There's 6 of them. And if you look at the reactant side, the only element that has, or the only molecule that has carbon in it is CO2. So right now, if you only have 1 CO2 and you've got 6 in a glucose, that doesn't add up. So you make yourself have 6 carbon dioxides. Okay? That's going to change your number of oxygens, but you're going to see that the number of oxygens is going to work out as well. Okay, so if we want to see if this is balanced, what we end up doing is we end up writing down all of our elements. And we end up writing the number of atoms of each of these elements to see whether they even out. So here we have an equation of sodium chloride plus fluorine, which yields sodium fluoride plus chlorine. Okay? So when you go about balancing an equation, and I'm telling you right now, this is not balanced. If we look right now, and we're going to prove that it's not balanced, if we look right now to see, first of all, are the same elements on both sides? Because if they're not, we can't do anything with this equation. So let's look at this. How many, let's write down all the different elements that are on both sides of this equation. So in this case, what elements do I have on my reactant side? What's that first element that we see? We see sodium. How many sodiums do I have? I only have one because there's no little subscript there and there's no number in front of it. Okay? What else do I have attached to the sodium? I have a chlorine atom. How many? I got one, and then what else do I have? I have fluorine. How many of those? Two. Okay. Now on this side of the equation, what do I have? I've got sodium. Do I have 1, 2, what? I've got 1 sodium. And I usually go in the same, I write the things down in the same order on both sides because it makes solving it easier. You don't get as mixed up. Okay, so let's look at our number of chlorine on this side. How many? 2, and fluorine. Wow, if I look at that right now, I can tell right away that that is in fact not balanced. Because I don't have the same number of chlorines on both sides of the equation, and I don't have the same number of fluorines. So here's the deal. I've got to add, I've got to try and find, okay? Notice how I left spaces in front of every one of those molecules. And that is because there's the opportunity there to add whole numbers. You can't add decimals. You can't say, oh, I'll put 2.5 of that. Okay, it's either 1, 2, 3, they're whole numbers. And you can add a lot of these. I've seen equations in the past where we've had 25